In the last video, we described light as being electromagnetic radiation that moves through space with a speed of 300 million meters per second. Experiments have shown that electromagnetic radiation exhibits the wave-like properties of reflection and transmission that we previously looked at in mechanical waves. When an incident wave hits a boundary, the wave will be reflected. In a similar fashion, when a light ray traveling in a medium, for example air, encounters a boundary leading to a different medium, for example water, part or all of the incident light ray is reflected back into the first medium. But what do we mean by the term light ray? In optics, when dealing with phenomena involving the interaction of light waves on objects, we are using what is known as a ray approximation method to predict and explain the characteristics of such interactions. Light traveling in a straight line within a homogeneous medium can be viewed as an infinite number of adjacent EM waves. At each point along the direction of the propagation, all corresponding points of all of the adjacent waves that propagate in unison can be schematically represented by an imaginary surface called a wavefront. A light ray is a line that is perpendicular to the light's wavefront. Alternatively, a light ray can be viewed as an imaginary line drawn along the direction of travel along the light beam. In the ray approximation, we assume that a wave moving through a medium travels in a straight line in the direction of its rays. So when a light ray traveling in a medium, for example air, encounters a boundary leading to a different medium, for example glass, part or all of the incident ray is reflected back into the first medium. Light reflected from a smooth surface is called specular reflection and produces parallel beams of reflected light as shown in the figure. This results in a sharp image in the reflection. In contrast, light reflecting off rough surfaces is called diffuse reflection and results in a blurred reflection. Experiments have shown that the angle θ1' of the reflected ray measured with respect to the normal of the surface is equal to the angle of the incident ray θ1, which is also measured with respect to the normal. The normal direction is the direction that is perpendicular to the plane of the boundary, just like we saw with normal forces in the forces chapter. This equality is called the law of reflection. A ray of light traveling horizontally strikes a mirror that is tilted at an angle of 36 degrees to the horizontal as shown in the figure. What is the direction of the reflected light with respect to the normal of the mirror surface? Since the incident ray is moving horizontally and the mirror is tilted at 36 degrees to the horizontal, it follows from trigonometry that the angle of incidence is 54 degrees with respect to the normal of the mirror surface. Therefore, the reflected ray must also be at 54 degrees with respect to the normal. So what's the angle of the reflected ray with respect to the horizontal? For the previous question, the angle of the reflected ray is 54 degrees with respect to the normal of the mirror surface. Thus, the reflected ray must be 90 degrees minus 54 degrees plus 36 degrees, or being equal to 72 degrees with respect to the horizontal surface. When a light ray within a transparent medium encounters a boundary leading to another transparent medium, then part of the incident ray is reflected, while the other part is transmitted into the second medium. What's also observed is that the transmitted ray is slightly bent with respect to the normal of the surface. That ray that enters the second medium is said to be refracted. To see why light behaves like this, consider the following thought experiment. Imagine that you're running at a fast pace and suddenly you run into a wall of water. You would suddenly slow down because water is denser than air. You would slow down even more if you ran into a wall of jelly. The denser the material, the slower you will run through it. Light experiences the same problem when moving from one medium to another. It experiences a change in speed. However, the change in speed of the light is not due to the physical density of the material, but rather its charge density. Substances with high atomic numbers will tend to slow light down more. This property of the material is called the index of refraction, or the refractive index, and is a measure of the retardation that light experiences as it propagates through the material. The refractive index is given the symbol n and is defined as a ratio of the speed of light in vacuum to its speed in the medium. It can be seen from the definition that the index of refraction is a dimensionless number that is greater than 1, since c is the maximum speed at which light can travel. In most cases, the refractive index of air is approximated as 1. As light travels from one medium to another, its frequency remains constant. Therefore, the wavelength must change because the speed has changed. If light passes to a medium with an index of refraction n, then the wavelength of the light is given by lambda n is equal to lambda divided by n. When light passes from one medium to another medium with a high index of refraction, part of the light is reflected at that boundary and part is transmitted. In the process, the transmitted ray will always bend towards the normal of the boundary. This is analogous to driving a car with one wheel on a smooth surface and one wheel on a grassy surface. The wheel on the grassy surface will experience more friction and will tend to slow down, causing the car to steer towards the grassy surface. The slowing down of the light in a high refractive index medium causes a decrease in its wavelength. As a result, the wavefronts in the high refractive index medium bunch up, causing the bending of the wavefront and leading to the bending of the ray towards the normal. The opposite is true when light is transmitted into a medium with a lower index of refraction. The light speeds up and its wavelength increases, leading to the wavefronts being further apart and causing the light to bend away from the normal. As such, the angle of refraction is dependent on the index of refraction between the two media. This relationship was determined experimentally by Wilbur Snell in 1621 and became known as Snell's Law or the law of refraction. Snell's law is expressed as n1 sin theta 1 being equal to n2 sin theta 2, where n1 is the index of refraction of medium 1 and n2 is the index of refraction of medium 2. Now let's apply this law in the following example. A beam of yellow light, which has a wavelength of 589.3 nanometers in air, is incident from air, which has a refractive index of 1, onto a smooth water surface at an angle of 35 degrees. So what is the angle of refraction if the index of refraction for water is 1.33? What is the wavelength of the refracted ray? Provided there has been a change in the wavelength of the refracted light, does this mean that the color of the light beam has changed? This value of light, when it travels between media with different values of the refractive index, is responsible for optical effects and illusions, such as why objects in water appear to be closer than they really are. Another interesting effect, called total internal reflection, can occur when light attempts to move from a medium of a high index to a medium of a lower index. Consider a light ray that passes from a medium of a high index n1 to a medium of a low index n2 at an incident angle theta 1. Some of the light is reflected and some is transmitted. The transmitted light is refracted away from the normal at an angle theta 2 that is determined by Snell's law. As the angle of incidence theta 1 increases, the angle of refraction theta 2 will also increase until it is 90 degrees with the normal as shown in the figure. The incident angle at which this occurs is called the critical angle. At this point, the refracted light travels parallel to the boundary as indicated by the refracted ray in the figure. At incident angles greater than the critical angle, there is no refracted ray and all of the light is totally internally reflected. We can use Snell's law of refraction to find the critical angle by setting theta 1 to be the critical angle and theta 2 to be 90 degrees. The sine of 90 is equal to 1, and Snell's law can be rearranged to give the sine of the critical angle to be the ratio of the low index of refraction over the high index of refraction. The critical angle is thus the inverse sine of the ratio of the two indices of refraction. A very interesting and important application of total internal reflection is the use of glass or plastic transparent pipes or rods known as optical fibers to guide light over long distances. Optical fibers are predominantly used these days in telecommunications, where optical signals are transferred down the core of an optical fiber through the aid of total internal reflection. In summary, when light hits a boundary between two transparent media, some of the light is reflected and some of the light is transmitted. The transmitted light is bent in a process called refraction. The property of the medium that causes refraction is called the index of refraction, which is defined as a ratio of the speed of light in a vacuum divided by the speed of light in that medium. The index of refraction for a vacuum is equal to 1, and the index for air is also approximated to be equal to 1. The index of refraction causes the light to slow down and also changes its wavelength. The degree of refraction is governed by Snell's Law. When light attempts to move from a medium with a high index of refraction N1 to a medium with a lower index of refraction N2, it is possible that it will experience total internal reflection. This occurs when the incident angle is equal to or greater than the critical angle for total internal reflection. The sine of the critical angle is equal to the ratio of the low index of refraction to the high index of refraction.